Hello folks, welcome back. So this is basically the roundup of the first week of reinforcement learning of a CNN or convolutional neural network, learning how to play DoomRL or DRL nowadays, the former Doom roguelike that has been renamed due to copyright and licensing issues. And if you were with me before, if you saw the previous videos, you saw that it took probably, I would say it took me about 3 or 4 days to come up with a training setup that was capable of guiding the convolutional neural network to gradually figure out how to traverse the level. And after letting that training regimen that took me about 3 or 4 days to come up with run for another 3 or 4 days, about 4 days, we had our bot for the first time descending to level 2. If you watch my follow-up video, you'll know that on the day after it descended to level 2 for the first time, it descended to level 2 90 some odd times. So that's pretty good. That's quite the ramp up from once over 4 days to 100 times in 24 hours. But it's still not very often, and there were still pretty significant signs that there were some bad patterns that persisted. But the next update, as I said then, was going to be over the weekend because I had to go back to work. Easter vacation was over, and so I haven't got much of a chance to check in on it. It's just been running along for most of the last week. And now I can show you a little bit about the results, talk you through the numbers, talk you through some of the numbers in the engine and what I've learned about this, and then about the next steps, because the big question we're going to have to ask ourselves is, looking at what we've done there in the last week, can we actually do better? And the answer is probably yes. So I'm going to move this thing over here. So I can see what you're seeing over here. Let me make myself smaller here real quick. That should work somehow like this. There we go. And now you can see what I'm seeing over on this screen. And here you will see that I'm looking at a replay screen of where the most recent training run ended. And in that replay screen at the bottom, I stopped right around the time where I have a snapshot that tells me to what extent this model would still be learning right now and to what extent it is basically crystallized. Now, one number that's interesting is the entropy loss is still relatively large. A value between minus 0.5 and minus 1 is usually a sign that the model has a relatively rigidly established pattern of behavior. That's not really a problem that we have here. But what we do see is we see an explained variance of 0.968. That means the model is very, very, very good at following its immediate incentives. It has a very clear idea of just how many points it might gain or lose when it does a given thing in a given situation. Yeah, the learning rate is fixed, and we've seen that it's run about 62, let me highlight this so it's easier to read, almost 62 million training turns, right? It has also run, this is, by the way, a false number. It says it has run 2,700 iterations. This is because I erase old replays. It doesn't actually know how many iterations it has run. In reality, it has run on the order of 50,000 plus iterations by now. So this number isn't entirely true, but it tells us how many iterations it has run since the last time I backed up the records directory. Now, there's a few other important things to look at. Remember, one of the biggest problems we had is the problem of the model parking on the stairs and then not actually knowing that it should hit the spacebar. And today, I'm going to explain to you exactly why that is and why this is such a particularly difficult step for this particular model. I already said that it's because the spacebar is not useful very often and gets punished quite a bit of the time, but the fact that it's not recognizing that this is the time to hit the spacebar is still very interesting. It tells me something about what parts of the screen the model has decided to focus its attention on and what parts of the screen the model is ignoring. We'll do a quick demo of that. Here, one thing that we see that is very interesting, if I go up here, now there's many runs where the worker eventually just died, and there's ones where, here, see, no, it killed an enemy, it reloaded. Yeah, it was probably even still alive when I interrupted that run. But up here we have a case, see, where it got to the staircase. Now this is good, this is quite good. Because I can see, oh no, he died. He parked in the staircase, then he died. Hang on. Hang on, hang on. He parked on the stairs. But then he lost too many points. Oh, here's a bad one. Here we can see. You can see here that even after another week of training, what you see me scrolling through here is all the times that this particular agent on this particular run was on the staircase and didn't hit the spacebar. So even after a week of us having an insanely outsized reward for hitting the spacebar when you're on the stairs, this agent sat there for a very, very, very long time. So did the agent make any progress in the last week? Did it get any better? How do we know if it got better? Well, for that, I can go back to my directory with all the training runs, and I can say, okay, yesterday at, let's say, 10 in the morning, 10:52, I have a timestamp here. Overnight, there was a time where it was turned off. Until this morning at about the same time, I have about a 24-hour period. If I grab all the runs from that 24-hour period, this is a relatively quick and dirty method because I'm too lazy to write a specific graph just for this. I will look at over here. I've actually already done this, but I'm retracing the steps just so you can see me actually doing it in front of your eyes. I will put in the runs that, oops, did I copy the wrong thing? I should have just done it the other way. 1 second. I'll let you look on at my fingers here. Shouldn't have done that. Okay, so copy, paste. And now I can see that in the last 24 hours, has it made progress since the beginning of the week? Absolutely. Back then in 24 hours, it completed the level 90 times. Now it did it 200 times in 24 hours. So definitely it is doing better. It definitely learned a bit more, but it certainly didn't complete it 1 out of 3 times or 2 out of 3 times, despite the fact that this level is extremely easy. Instead, it completed it. If you look at the run numbers, these here are the run numbers. You can see that out of 100 runs or so, or out of 1,000 runs, sorry, it completed it maybe 15-ish times here, right? So still a very, 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 very high failure rate. Definitely nowhere close to actually completing the level in a particularly deliberate or regular fashion. Now, why is that? Well, here's the thing. The model I'm using here is not dumb. It's not a primitive model. The convolutional neural networks are some of the networks used for amazing image recognition. They are also used, and this may surprise you, they're sometimes used in very powerful chess engines. They have been used to play in Go tournaments. But what they lack, what is very important to understand about a CNN, is it has no memory. So you have to distinguish between training, the sort of memory burned into a model during training, and then situational memory of what it is actually doing right now. And the fact is that convolutional neural network has absolutely no memory whatsoever of what happened before at any given turn. Why does this not matter when you're playing chess or Go? Because in chess or Go, at any given point in time, the entire game state is directly in front of you. It's captured in this, in chess's case, relatively simple matrix, right? And in of 8x8 squares, and in Go of a bigger matrix of more squares. And it was, of course, at the time when we were training the early CNNs, it was a big, big, big milestone to be able to play chess. It was a big, big, big milestone to be able to play Go. But you have to understand that from the perspective of the problem that, from the perspective of CNN, Go and chess are like an ideal scenario because at any given point in time, you can derive what the next best move is entirely from what you're looking at right now. And you have to have no idea whatsoever what came before. So why does this not work for what seems like a much simpler game like DRL? Well, in order to figure that out, let me show you something real quick. Here we have DRL. This is the ASCII version. This is what the bot sees. It's not the graphical version. I have started up here. This is what I see at the beginning. This here is a tree. This here is like a red field. Here's a gray field, like normal tiles. This is the building walls, right? Now, if I'm a bot and I see the door, oh, there's a human. So one thing the bot is definitely learn is, oh, there's an H, something is moving there, it looks like that, I should shoot at it. The bot does this quite reliably. Sometimes the bot also notices that there's a door here, and it will notice this despite the fact that there's stuff lying on top of it, or maybe it won't notice it anymore when there's stuff lying on top of it. And it will move towards the door. So this is basically what it looks like when the bot is successfully clearing the level. Well, what happens when the bot doesn't happen to find this door despite the fact that we've trained it a little bit? There's still a chance of it just sort of walking over here. And by the time the bot has walked over here, it has much less of an idea what it's doing. It's no longer clear to the bot exactly how it might get to the door. I'm actually kind of surprised the bot seems to have a pretty good visual awareness. If this is what the bot sees, it might still be able to find the door. But at this point, various magnets that we have might not be helping the bot very much, because the bot could be over here, it could try to walk towards the door, it could run into a wall. And the other problem that we have in the case of this general incentivization is the bot, when you're playing level 1 over and over again, always starts over on the left somewhere, and always has to move over to the right somewhere. So in general, from the beginning of the game, the bot is always incentivized to move to the right. Then it sees a door, it moves to the right, then it moves through the door, it moves to the right. So what happens if by some random chance, because it's distracted, the bot wanders too far over here? Well, in general, the chance of it trying to move to the right is higher than the chance of it trying to move to the left, because it has gotten this far by generally moving to the right. So it's much more likely to get stuck over here, and this is what happens a lot of the other run. Another thing that happens a lot of the other runs is just that it gets shot. It usually gets shot at the latest at the time when it runs into its first shotgunner. This level always contains one guy with a shotgun. The guy with a shotgun is harder to kill than a guy with a pistol, although I think I might have accidentally taken him out here already. If the bot doesn't immediately shoot the guy with the shotgun and hit and does it quickly, then the bot dies. So if the bot is busy chasing a door, it dies. Then now, here's the biggest hurdle, okay? In order to pick something up, let's see, I can press G to get an item from the ground. Now I have that item, but I don't have it equipped. There could be a shotgun, and if I could pick it off the ground, but then I still don't have it equipped. In order to equip it, I have to hit I. Now I'm on a different screen. Now I have to remember that what I was trying to do was equip the shotgun, at which point the model falls apart, because it has no way to tell why it got onto the screen. That means it has very, very, very few chances where it could possibly even learn or divine that in this screen there are certain things it might want to pick that are better than others. And even if it did realize that something is better than something else, it would likely make bad mistakes later on. So for example, suppose that I've walked into a room and the room is full of demons and I have a shotgun, but I realize that in a room full of demons, it's better to have a chainsaw. Well, I might have a chainsaw in my inventory, but if I open my inventory and in my inventory I see a chainsaw and a rocket launcher, maybe I've learned along the way that a rocket launcher is more powerful than a chainsaw. And I've forgotten that I'm in a room full of demons who are directly in front of me, so I might equip the rocket launcher and shoot it at the demon in front of me, because by the time I get back out, I've forgotten that I picked up the rocket launcher, I shoot it at the demon in front of me and I blow myself up. That sort of thing is going to happen to this model invariably, and there's basically nothing that it can do about it. So how do we get around this? Well, in order to get around this, we now need to give the model a memory. And there's 3 ways to do this. One is, on the one hand, extremely primitive and extremely expensive, and on the other hand, extremely effective, and it's exactly what the LLMs that you're talking to, or very similar to what the LLMs that you're talking to actually do, which is, I could, instead of letting the model see one frame at a time, similar to a chessboard, I could actually let the model see the entire history of frames and recalculate what is going to move going forward based on every single frame it has ever encountered. There's one big problem with that. I would run out of memory. It would start to take years for the bot to decide what to do next if it's running on a single processor. And this is why, by inference, this is why having a longer conversation and more context when you're talking to an LLM gets so much more expensive, because the way that the LLM acts as though it remembers the history of the conversation is that it gets the entire text of the entire conversation dumped through it every single time you hit enter on your prompt. And that creates the impression that it knows what happened before, even though it is in fact a new set of processors seeing the world for the first time and then churning through your entire conversation at once to spit out the next most likely best answer. In this particular case, we could do that by basically sending it every single frame buffer, but that's very, very expensive. In fact, when Google trained a CNN to play Pong, which they did successfully, they did it by only giving it 4 previous game frames. So they gave it 4 game frames, and that was enough, or maybe even just 3, and that was enough for the bot to detect the motion of the ball, right? And as long as it can detect the motion of the ball, the direction and the velocity, then it can decide how to move the paddle. And it can also realize how quickly it can move the paddle and how slow the paddle moves based on the last few frames. So it can see in a given frame, how far can my paddle move relative to how fast the ball is moving, and what am I going to do based on that? That works, but it's very little information, right? It's a few dots. Pong is a very simple game. And so passing in a few frames for it to detect the velocity of this thing is a relatively small amount. On this screen, this is not a complex screen, but we already have a lot of more material than a Pong game to deal with, and passing in order to piece together a strategy, like the fact that I maybe have a health orb sitting somewhere and I leave it there because I need it for later, because I first want to lose more health fighting enemies, and then I go back and grab the health orb, stuff like that. I would need to pass in like the last 1,000 turns or something like that this thing took. So that's not gonna be viable. And here's the other thing, and this is now specifically getting to the stairs. You see, that there is the stairs. Now, the bot has probably figured out that generally speaking, it wants to move towards doorways, and it has probably figured out that generally speaking, it wants to move to the stairs. The problem is, once it's on the stairs, it can't see them. It doesn't know that it just moved there. Now, in order to figure out that it should do something because it's on the stairs, it would have to look up here. The problem is that in addition to, and by the way, it can't actually read. It can detect that there's different stuff here now, but it can't read per se. So in order for the model to decide to actually press spacebar, it would have had to recognize somewhere along the way that that is actually determined by what's up here, right? Rather than by something that it sees down here. But it spends the entire rest of its time responding to what it sees down here, not what's up here. So that's why it sucks at DRL. And that's why we definitely need to give it some form of memory. Okay, now we've talked about putting in frame buffers, just basically giving it all the previous turns and seeing if it mathematically starts to think ahead. That's incredibly expensive, like I mentioned before. There's 2 other ways, 2 other models that we can use here. One is called a GRU, and one is called an LSTM, a long-term, short-term memory model, or I don't actually know what GRU stands for, sorry. The reason I don't know what it stands for is because I looked at the options and I dismissed it, because it turns out with the setup I already have running with PyTorch and the PPO trading setup, it's much easier to just use an LSTM. Does that mean, what's the difference? The difference is basically you still have a CNN there, but along with it, you have a mechanism, and I'm not going to describe it in too much detail, but you have a mechanism for an LSTM to basically store a string of numbers that it can use to keep track of history. And over time, the LSTM has to learn what's important enough to put in that string of numbers, in this like large array of numbers, and it has to then learn what decisions to base off of it. Now, that's a very complex problem for it to solve. It's going to take a lot of turns for it to start to come up with actual strategies there, but it's the only way forward. And it's much, much more efficient than passing in like 1,000 game frames and letting it try to compute the next state based on some giant history it has to first sort through. So how do we do it? How do we prevent the thing from having to start over completely? How do I make sure that at least some of the 2 weeks of processing that I've just done are actually reusable? Well, let me go back here to the screen here. And this is where this box at the bottom becomes important. Again, even though this bot sucked at using the stairs, even though it still did a couple 100 times a day, oh my God, that is just crazy. So it still knows how to, within the incentives that I prescribed, that I described, predict the score it gets for its next move or for it next does with the keyboard, with its virtual keyboard, 96.8% of the time, which means it's basically learned as much as it can learn, including burning in some of these behaviors that are not ideal that I was just talking about, and not learning the menu. So it is definitely valuable for the LSTM to learn the stuff that this thing knows and then to start finding some way to shape its own understanding or strategy about what history might help it do better, what memories might help it do better. There are two ways to do this. One is called a teacher-student setup, where basically I would now take the CNN, this kind of dumb model, but ramped up one, and I would let the CNN and the LSTM at the same time. What would happen is that every single turn, the LSTM would try to make a decision. It would sort of decide what to do next and pretend to do it. The CNN would look over its shoulder and decide that that was either what it would have done too, or that it was the exact opposite of something that it would have done that it thinks is really bad. And it would generate a score that tells the LSTM that was really bad or that was really good, do more of this. And that would gradually, these two models would converge and behave in the same way. Now, that would be okay. That would take about a week, maybe, or maybe less, maybe more. And at that point, the LSTM would be behaving the exact same way as the CNN, and that will be then it would start to get better than the CNN. At some point, the LSTM, because it remembers things, might try to deliberately do something that the CNN wouldn't do, and it would think it's right. And at that point, there was a score that would start to a number that would start to go up that we could actually use to freeze the training and say, okay, at this point, the LSTM is trying to do things better than the CNN was able to do them. So let's decouple the CNN and the LSTM can just roll. But there's actually a faster way to do this. The faster way to do this is to take the training weights we already have, find a way to convert them so that the LSTM can read them, and then let the LSTM run with the behavior of the CNN and just continue from there. But right now, this CNN has spent 60 million turns learning not to open menus because it can't figure out what to do in there anyway, and not to use the spacebar. And the LSTM is going to have to break those habits. So what do we do? Do we have anything that we can do to make the LSTM more likely to figure out how to use the spacebar and how to develop better habits? Well, it turns out the answer is yes. The way we do this is the following. We have a variable. One variable that really matters a lot in this setup that we can use to make a chess bot suck. Let me explain. This one right here, oh, actually, sorry. This one right here is the entropy coefficient. The entropy coefficient is basically an instruction that tells the model that this fraction of the time, so in this case 1% of the time, it should do something completely random, no matter what it thinks is the right move. Why did I say that that makes a chess bot suck? Because in chess, you may have realized, if you play a lot, that a single move can very likely fuck up an entire game if you don't know what you're doing. So you could fumble your queen. You could make other really massive errors that allow someone else to get a much better position in one turn. It's very, very easy to blunder a chess game in one move. There are really obvious dumb blunders that beginners make. There are subtle blunders that might lose you a piece 2 turns later that even a more advanced player might make. And because it's so easy that for a blunder to wreck an entire game, I could take Stockfish that is perfectly well adjusted and can beat almost any chess master, or can beat any human chess master with ease. But I could inject this coefficient that says that at least 1% of your moves, or 5% of your moves, or 10% of your moves are just randomly moving some piece on the board. And that would pretty much handicap the shit out of it, right? At that point, it would be basically, it would have its strategy completely wrecked on every 10th move on average, and then it would have 9 moves on average to try to recover from that mistake, and then it would, on average, make another mistake, or it might make 2 terrible moves in a row. You never know how long this is going to take. It might play a perfect game here and then have 3 blunders in a row in the next game. It would definitely handicap the shit out of it. But for us right now, this coefficient is incredibly important, because we can now use this coefficient to increase the number of times that this new model, after it's ramped up, would make a completely random move. And by doing that, we can get it to organically rediscover menus. And if it uses a random button to get into a menu, then it has to also figure out how to get out of the menu. It might realize that something changed. Like if it was the inventory menu, it might realize that something changed afterwards. It did more damage, it did less damage, it no longer had a weapon, it was wearing armor, it took whatever, yeah? And then it has a chance to build that kind of situational awareness and realize that menus can be helpful. That's something that it would probably not learn on its own. So basically, this is the coefficient that we use to take burned in bad habits from the CNN and burn them back out. And we can do that for a while. And in this game, it's pretty forgiving because this is not chess. And in this game, you can do some pretty stupid things. One move where you don't dodge, even though you should dodge, is not going to mess up your game too badly, provided that you have the bigger gun, right? So we can set this reasonably high, like say 5%, and that is enough that the new model would be likely to rediscover patterns that the old model has given up on and be able to build on them because it has a memory. Okay, so that's what we're going to do. And in a week, I'm going to give you the next update. Cheers.